Good morning, everyone. Today I am going to explain how different solid materials are made. In simple words, how do powders turn into useful things like ceramics, magnets, coatings, and crystals? That's what synthesis, processing, and fabrication methods mean. The image at the bottom, the picture shows small colored particle on the left. These are raw powders. Then you see a big arrow called solid state reaction, meaning that we heat them. On the right, you see new bigger particles, that is the final solid material. So the image is basically saying powder plus heat gives us new solid material. Now I will explain the oldest and simplest method used to make the inorganic solid materials. This method is so basic that people jokingly call it shake and bake or beat and heat method. What do we do in this method? We simply take the powdered chemical we want to react, mix them nicely, sometimes press them into a pallet, then put them in furnace to heat for a long time. That's it. No complicated instruments, no fancy technology, just mix and heat. But even though it sounds simple, this method is extremely powerful. In fact, almost all the early high temperature superconductors were discovered using exactly this technique. But there's a catch. These reactions are inherently slow. Why slow? Because even if we mix the powders very well, the mixing is only good at the particle level. At the scale of about 1 micron, but at the scale of 1 micron for the particle. But at the atomic level, the atoms are still far away from each other and unevenly distributed. For the reaction to happen, the atoms of one solid must somehow travel into the other solid. This happens in two pathways: solid state diffusion, where ions very slowly move from one particle into another; liquid or gas transport, if the small liquid or vapor forms during heating, atoms can move faster through it. Only when atoms of two reactant reach each other in correct ratio and they finally form the product. To make this more clear, let us look at the common example, the reaction of magnesium oxide and aluminium oxide to form magnesium aluminate spinel MgAl2O4. On paper, this reaction looks simple, but inside the furnace, many small steps are happening. The two powder touch at certain points, tiny nuclei of new product form at those boundaries, and ions have to move across the interface. The new thick layer thickens slowly, and the final spiral grows only when enough ions have crossed over. So even a simple mix and heat reaction actually has a lot of microscopic processes going on behind the scenes. This is why solid state reaction need high temperature and long heating times, because the atom in solids move slowly and they need time to find the right partners and form the correct structure. So different forms of inorganic solid, example alumina, has been shown in the table in the form of an image, like the solid form of ceramic. The solid form of ceramic of film is showing the properties of dielectric substrate and applications in the dielectric substrate, fibers, saffron insulation, wools, etc. Now let's look at what actually happens when MgO and Al2O3, magnesium oxide and aluminium oxide, react to form the product MgAl2O4, also called spinel. Whenever grains of MgO and Al2O3 touch each other, everything needed to form the new compound is already present at that tiny contact point. So the very step is the birth of tiny crystals of the product. This step is called nucleation. But these baby crystals cannot be too small. If they are only 1 or 2 atoms thick, they collapse immediately. To survive, they must reach a certain critical size, usually several tens of angstroms, which means that they must contain many tens of atoms. This happens because two energies are fighting each other. Forming the product lowers energy, which is good for the formation of crystals, but a very small surface increases energy, which is bad. If the nucleus is too small, the bad surface energy wins and the nucleus disappears. So nucleation is naturally difficult. You need many ions to arrange themselves in correct pattern before the nucleus becomes stable. Now the process becomes much easier if nucleation happens on the surface of another solid. This is called heterogeneous nucleation. It's like building a house on a strong foundation instead of floating in the air. If starting material and the product have somewhat similar structures, the nucleations become even easier. In MgO and Al2O3 reaction, we have two good surfaces for nucleation as shown in the picture. Right hand side top picture, A and B. Then case A, the picture, the A part of the picture, at the boundary between MgO and spinal, the oxygen layer have the same type of stacking called ABC stacking, which means the cubic close packing. MgO has a rock salt structure where Mg divalent cation sits on in all the octahedral holes. The spinal has a similar oxygen arrangement, just with the Mg in tetrahedral sites and aluminium in half of the octahedral sites. Because the oxygen framework is almost the same, forming the first layer of spinal on the top of MgO is very easy. This is a three-dimensional structural match and we call this type of growth topotaxy. Nucleation on the aluminium oxide surface as shown in the B part of the picture. Here the oxygen layer are arranged differently. In the aluminium oxide, it has an AB HCP stack instead of ABC cubic stack. But along the two-dimensional interface, the oxygen pattern still lines up reasonably well. This is enough for oriented nucleation to happen, but only in two dimensions. This is called epitaxy. So what is the difference? With MgO, the product aligns in three dimensions, which is topotaxy, and the aluminium oxide, the match is only at the boundary, which is epitaxy. These relationships are very important in solid state chemistry because they tell us how easily one structure can grow on another. A beautiful analogy is shown in the bottom right picture, Escher fish to bird drawing. At the boundary between the fish region and the bird region, you can see the shape that look partly like fish and partly like birds. Similarly, at the atomic interface between two solids, the arrangement may have different features of both structures, not fully one or the other. Now, oriented nucleation happens easily under two conditions. The right atoms are present near the surface and the spacing between the ions in both the structures matches well. If the match is good, the interface is smooth and coherent. If the match is bad, the strain becomes too high and new nucleus breaks away. In MgO Al2O3 system, the interface match is good because all three structures MgO, Al2O3 and spinal have close pack oxide layers. So very thin layers of spinal can form easily wherever the grains touch. But making of the very first few layers in is the easy part. The difficult part is the growing of a thicker layer. Now, why is it difficult of growing the layer thicker of the spinal? Because now MgO and Al2O3 are no longer touching each other directly. They are separated by the spinal layer as you can see in the image which is depicted at top right corner. So for further growth, ions must travel through the already formed product, which is like trying to walk through a wall. This requires a slow complicated process called counter diffusion. Mg2 positive ions move away from the MgO side and Al3 positive ion move towards it like this. The movement is depicted by the usage of arrow. So, and they must move in such a way that the charge balance is always maintained. For every 3 Mg2 positive ion moving in one direction, the two aluminium trivalent ions must move in the opposite direction. The chemical equations written in the text describe what is happening at each interface. When we combine both interfaces, the overall reactions become 4 MgO plus 4 Al2O3 gives 4 MgAl2O4. Because of the different ion speeds, one interface moves faster than the other. If the two solids are different colors, we can actually see the boundary shift in experiments, and this is known as a Kirkendall effect. This reaction is extremely slow because ions like Mg2 positive and Al3 positive diffuse very slowly in solids. To make pure spinels, you might need to heat at 1500 degrees Celsius for one whole week. Defects like vacancies help iron to hop from place to place, but hopping is still rare, which is why high temperatures are required. This also explains why solid state reactions sometimes stop before completion. Once the reactant gets separated by product layer, further reaction becomes nearly impossible. To speed up the reaction, one useful trick is to take the partially reacted mixture, grind it again, and heat it once more. The grinding breaks the thick product layer and exposes the fresh surfaces of magnesium oxide and aluminium oxide so that the reaction can continue. Another trick is to use a small amount of gas or liquid that can carry iron faster than solid diffusion. Even a tiny amount of such transporting phase can drastically speed up the reaction. Now let's talk about Now let's talk about the difficulties we face when making spinels MgAl2O4 using solid state reaction. The biggest problem is that both MgO and Al2O3 are extremely stable and non-reactive solids. Think of them like very two stubborn people who refuse to talk to each other. Because they don't react easily, forming spinels become very slow and difficult. Solid state reaction becomes much easier when at least one of the starting material is more reactive or has ions that can move easily. But when both are stubborn, like MgO and Al2O3, everything slows down. Apart from low reactivity, we can face other issues too. Like some reactant may evaporate during heating, for example, like alkali oxides, PbO, bismuth oxide, mercuric oxide, and some material may attack the container and react with it, especially those containing transition metals. But with careful planning, we can manage or avoid these problems. To plan any solid state reaction properly, we must consider four main things: the starting material, mixing method, the choice of heater, and the heating or firing schedule, we mentioned in this slide. So, if we're explaining each of them briefly, our starting chemical should be pure, have exactly known composition, and should be ideally reactive. Sometimes this becomes difficult because some reagent absorb moisture or carbon dioxide from air, and this can change their composition without us noticing. Also, if the reagent contains transition metals, their oxidation state may be uncertain. So we often need to dry the reagent at the right temperature and store them in a desiccator to keep them moisture free. Desiccator is an instrument which absorbs the water molecules from its atmosphere so that anything which is kept in it becomes moisture free. So it absorbs the water vapors which is present inside the air in the desiccator. So for making oxide, it is often better to use oxy salts like carbonates, acetates, or nitrates. Why? Because they decompose during heating, releasing gases like carbon dioxide and nitrogen dioxide. The gas bubbles help break the powder into smaller particles, increases the surface area, and make the reactant more reactive. So the reagent like these are shown in the solid state reaction synthesis method in this, in which the um, carbonate, calcium carbonate, and other material are used to make the precursor material for the solid state reaction. This is like fluffing up flour to make mixing easier. Now for the second thing, that is mixing of reactant, which is get them as close as possible. The solid state reaction only happen where the particles touch. So we mix and grind these powder extremely well. We can do this manually using mortar pestles or using mechanical mixers like Miller balls. Like in this picture, the Miller ball mixing is shown at 300 rotation per minute for 4 hours, and in this manual method for grinding the particle to finer size so that they come close together to react uh, is shown in this picture. So the ball milling works by rotating the jar with the agate balls inside. The balls hit and grind the powder, reducing the particle size and ensuring intimate contact. High energy planetary mills work even faster, but they have a risk. The milling ball or jars can contaminate the sample. Often we add a small amount of water or organic liquid during mixing to make the grinding smoother. But after mixing, we must dry the powder completely. So for the next thing, that is the choice of container, it must not react with the container. The container for heating must be chemically inert. For oxide synthesis, the commonly used container are platinum, which is very inert but reacts with the Li2O, BaO, and many transition metal oxides. And another one is gold, which is more inert than platinum but melts at 1063 degrees Celsius, so cannot be used for very high temperatures. Also, alumina crucibles which have high melting point but may cause slight contamination. Silica crucibles stable up to 12 100 degrees Celsius but react with alkali oxides. And graphite crucibles used for sulfides, chalcogenides, and nitrites. So the container depends on the reaction chemistry. Next, firing schedule, heating carefully and intelligently. The heating plan must be designed to allow smooth decomposition of any carbonate or nitrate reagents. Avoid melting or evaporation of reactants and hold a temperature where the reaction can actually happen, usually 12 to 24 hours. We can heat in open air, controlled atmosphere in a tube furnace, or a sealed silica metal ampoules to prevent evaporation. For well known material, literature recipes help. For new material, we often rely on trial and error method. Now let's look at examples that require special care. For example, lithium silicate. The reaction is written as shown, and the condition, which is it occurs at 800 degrees Celsius, and the time taken for the reaction to complete is 24 hours. The problem is that the lithium carbonate melts and decomposes above 720 degrees Celsius. This is because the size of lithium is very small and it polarizes the big anion it is attached to, which is carbonate, and causes the carbon dioxide to evolve. So it decomposes at lesser temperatures and it reacts with almost every container material like platinum, silica. The solution is to use gold crucibles. First, preheat to decompose the lithium carbonate at 650 degrees Celsius for few hours, and then fire at 800 to 900 degrees Celsius overnight to get the final product. The next example is YbCO superconductor. The reaction is already written as shown, and it occurs at 950 degrees Celsius. Um, and for it takes 350 degrees Celsius for oxygenation. The problems associated is with this that is barium carbonate is extremely stable, which is one of the precursor for this reaction to happen. It gives off carbon dioxide very slowly, so the reaction occurs slow. The product YbCO can react with the carbon dioxide in the air and lose oxygen, reversing the reaction. And copper oxide react with many container materials at high temperatures, and a high temperature is the requirement for the reaction to occur. Also, the product YbCO has variable oxygen content. So the oxygen must be exactly correct, otherwise the superconducting temperature drops. The solution for this is reacting in a carbon dioxide free atmosphere and use barium nitrate instead of carbonate to avoid carbon dioxide problems, and make pellet of the mixture and place them on a bed of YbCO powder to avoid contamination. And after heating at 950 degrees Celsius, perform the oxygen annealing at 300 degrees Celsius to let the material absorb oxygen and reach the perfect formula, which is YbA2Cu3O7. Now let's discuss the method that is complete opposite of slow high temperature solid state reactions. In solid state synthesis, we usually heat powders for hours or even days. But in this next set of reactions called combustion synthesis, self propagating high temperature synthesis, SHS, and solid state metathesis, which is SSM, the reaction is so energetic that it actually behaves like a controlled explosion. And the amazing part is the product form in minutes or even seconds. Let us discuss how this works. So SHS, which is the reaction that feeds itself. In this method, which was developed by Marzanov's group in Russia, relies on choosing the reactants that react very exothermically. That means that once you start the reaction with a spark or small heating, the reaction releases so much heat that it keeps itself going, like lighting one end of a matchstick. In SHS, the starting materials are grouped into fuels and oxidants. A classic example is the thermite reaction used in industrially to extract iron, which is shown here. Here, aluminium act as the fuel and Fe2O3 act as the oxidant. Once ignited, the reaction shoots up to nearly 3000 degrees Celsius for a short period of time, hot enough to melt iron. That short burst of heat is enough to complete the entire synthesis. In other combustion reactions, fuels like urea, glycine, or hydrazines react with metal nitrates, which serve as oxidants. Nitrates, which serve as oxidant. These fuels don't appear in the final product, they burn off during the reaction. The example of combustion synthesis is the spinel, which is shown here with different stoichiometrics of nickel, zinc, FeO. So, a well known example is the combustion synthesis of nickel zinc ferrite spinel. We mix the metal nitrates and urea in exactly the right ratio so that the maximum energy is released. When the mixture is heated to around 600 degrees Celsius in the silica crucible, it self ignites, no external heating needed, and the spinel forms almost instantly. Because of the reaction produces gases, the powder formed is extremely fine and fluffy. Later, we can press this fine powder into pellets and heat them to make dense ceramics. The temperature control is important. Below 1100 degrees Celsius, the ceramic does not densify completely, and above 1300 degrees Celsius, the grain grow too fast, called exaggerated grain growth, making the ceramic uneven. For the other method, that is SSM, solid state metathesis, work in a very similar way, but the driving force is different. In SSM, the reaction is powered by the formation of a side product with very high lattice energy, usually an ionic salt. For example, the reaction shown here, in which the Li3N and the TaCl5 reacts to give the product, the formation of a lithium chloride, which is highly stable, provides the energy that drives the reaction forward. After the reaction, the lithium chloride can be washed away, leaving behind pure TaN. The SSM reactions are actually easier to control than SHS reaction because the temperature cannot rise above the boiling point of the side product. For example, once lithium chloride starts boiling, further heating is naturally limited so that the reaction doesn't overheat. These reaction results in the making of carbon nanotubes in seconds. SSM reaction can make extremely advanced material. For example, the reaction which is shown here, in which the lithium carbide reacts with the C2Cl6 to give the product. This produces carbon nanotubes. This 8C, this is the carbon nanotube, both single walled and multi walled bamboo type nanotubes, in just a few seconds at temperature over 2000 degrees Celsius. This shows how powerful the SSM method is. Material you can make with SHS using these rapid self heating reaction, we can prepare carbides, which is shown here, which is shown here, and silicides, and sulfides, oxides, phosphides, and many more oxides. In all these cases, we have to do preliminary tests to optimize the exact ratios and reaction conditions, but because these reactions are extremely fast and we must tune them carefully to get phase purity and high quality products. In this picture compares the three different type of combustion synthesis method. All three method produce solid material using reaction that release a lot of heat, but they differ in how the reaction is started and how it proceeds. For the part A, which is cell propagating high temperature synthesis, we start with a dry solid mixture of a reactant. This mixture is only heated to one point, usually at the top, for using this filament heat energy. And once the top layer catches fire, the reaction becomes so exothermic that the combustion wave travel on its own from the top to bottom, and this wave produces the product as it moves downward. So the key idea is one small ignition starts a chain of reaction that spreads by itself. It shows a dry bed, powder bed, solid reactant, a heater that touches only one end, which is igniter, and the arrow going down shows combustion wave propagation. And the bottom image, this the final product left after the wave has passed. For part B, it is volume combustion synthesis. In VCS, instead of igniting just one point, we heat the entire container uniformly. When the mixture reaches a certain temperature, the whole volume ignites at the same time. So instead of wave traveling from one end to the other, the entire container undergoes combustion together. For part C, which is solution combustion synthesis, the reactant are dissolved in water along with a fuel like urea. So this method starts from a solution, not a powder. And then we heat the beaker, water evaporate, and the mixture becomes a thick gel around 200 degrees Celsius. The gel suddenly catches fire and burns rapidly. This is the combustion step, and the burning gel produces a fluffy fine powder of the final, which is the final product, which is shown here also, in which the fuel and water are mixed together, which are metal precursors, and at 80 degrees Celsius the formation of gel take place, and above 200 degrees Celsius the combustion of gel. The gel starts to catch fire, and the combustion of gel leaves us with the product, which is as burnt powder, which is fluffy fine powder of the final product. Now let us discuss a completely different kind of solid state reaction called mechanosynthesis or mechanochemical synthesis. Normally solid state reactions require very high temperatures to make atoms move and react, but in some favorable cases we can actually make reactions happen just by grinding the solids together without heating the sample at all. This is done using high energy milling. For example, in ball mills, like the mechanochemical synthesis using ball milling products is shown here. Substrates, ball milling, and the new product is formed, ball milling method. So the high energy milling, for example, in ball mills, where the powders are shaken, hit, and crushed repeatedly for several hours. And of course, we must be careful because the milling media, like the agate or steel balls, can sometimes contaminate the sample. Even though no external heat is applied, the intense mechanical action does several interesting things. The powder become extremely small, and the particle size are crushed down to nanometer scale, which dramatically increases the surface area and reactivity. And the crystal defects are created. Mechanical impact creates dislocations and vacancies, distorted crystal regions. Thus, these defects act as fast pathways for the atom to move. And although the overall sample is not hot, but the mechanical energy converted into heat locally at the point of impact, these microscopic hot spots speed up the diffusion and help the product form even at the room temperature. Because of these effects, the mechanosynthesis can form, and the product phase on the product phase. The mechanosynthesis can form the product phase on a very fine scale without using a furnace. The product from mechanosynthesis behave differently. The material formed by these methods are often not the same as those made by the normal solid state heating. They may be metastable, structurally distorted, and compositionally inhomogeneous, containing large number of vacancies. This is because the reaction happens under a very non-equilibrium high energy condition. A good example of this synthesis is Zn2 SnO4 nanoparticles, which is shown here, which is an inverse spiral. So, when the material was prepared by mechanochemistry and analyzed using diffraction microscopy and spectroscopy, the core of each grain had the correct inverse spinal structure, but the outer shell showed ZnSn mixing and distorted polyhedra. This clearly indicates that the particle formed under non are formed under non-equilibrium conditions with significant disorder, something that does not happen in normal high state temperature synthesis. And why is it important? Because the structure of materials made this way is different, their properties can also be different, and different properties, the manipulation of these properties into physical world is always a high scope for research. So this can be an advantage, especially for making nanomaterials that need small size, high defect concentration, unusual structures, or enhanced reactivity. Mechanosynthesis is also cheap, energy efficient, and able to create material that normally require very high temperature for long periods. So overall, mechanochemistry is becoming a very important technique for making new nanomaterials, nanocomposites, and even bulk material that would otherwise be difficult or expensive to prepare by conventional methods. So for the next discussion, till now, we saw that solid state reaction, including mechanosynthesis, have a big problem. Even if we mix powder very well, they are not mixed at the atomic level as discussed earlier, and the atomic level mixing is essential for fast, clean, uniform reaction. This is why scientists developed several low temperature methods, low temperature methods also called chemi or soft chemistry methods. These include reactions in gases, liquids, and even some special solid reactions. They mix the reactant at almost atomic scale, so reaction become much easier and cleaner. These soft chemistry routes have several advantages, including greater purity. Because we avoid long high temperatures heating, there is less contamination from the furnace or container. Excellent chemical homogeneity, that is, all the atoms are mixed very uniformly, and this improves the material properties and help us understand how structure, dopants, and composition affect behavior. Also, the different shapes that are possible to form by this method, we can make fibers, films, coatings, and not just powders. This is very useful for electronics and optical devices, but there are some disadvantages also, that like the chemical reagent are often expensive, they are unstable or difficult to handle, and a lot of research is needed to optimize the recipe for the formation of that particular solid mixture, and a method that works for one compound may not work for another closely related one, which creates a discrepancy in the synthesis of the same kinds of solids. So, in practice, most researchers still try simple solid state reactions first because they are quick, cheap, and versatile. But when we want better purity, better homogeneity, or special forms like coating, then soft chemistry methods are used. Now, let us discuss one of the most powerful and widely used soft chemistry method, which are the alkoxide sol gel method. So the sol gel method is like turning liquid into jelly and then heating the jelly to get the solid ceramic powder. The first step is to prepare the homogeneous solution with all the metal ions mixed in the exact ratio we want. This is much better than the powder mixing because now the atoms are mixed molecule by molecule. As shown in this picture, the precursor and the solvent mixing, the transparent solution is formed. And then the solution slowly thickens into a sol which contains extremely tiny particles, colloidal size. And if we keep drying it, the sol becomes a transparent gel, which is shown here. The mixing and evaporating after the hydrolysis and polymerization of the precursor and the solvent which are mixed, the sol is formed, and the evaporation of it gives us gel. This is basically a solid network with liquid trapped inside. The important thing is no crystals should form at this stage. We want a smooth, amorphous, uniform gel. In the final step, we heat the gel. This heating removes water, organic groups, and hydroxyl, and the amorphous just crystallizes into the desired oxide material. So the steps are solution, sol formation, the gel formation, and then oxide. So there are mainly two types. First is alkoxide based sol gel, which uses organometallic precursors, and the other sol gel routes depending on the material and application. So the alkoxide based sol gel is the most common method in which the liquid metal organic compounds called alkoxides are used. And some of the common examples are tetraethyl orthosilicate, which is the source of SiO2, titanium isopropoxide, which is the source of TiO2, and aluminium butoxide, which is the source of Al2O3. These are covalent to liquids, so they mix well with alcohols. And we add water, usually a little acid or along with a little acid or base, so that hydrolysis occurs. So the key steps, one of the key steps are hydrolysis. The OR groups are replaced by OH group, and this produces the molecule like SiOR3OH and SiOR2 and OH twice, and so on. The second step in condensation, in which the OH group react with each other of different molecules to form MOM bonds. This gradually builds the 3D network. If we are making a mixed oxide with more than one metal cation, cross condensation must occur, which means that MOH of one molecule combines with the MOH of other molecule which is not same, and MOM dash is formed. This ensures that the metal is uniformly mixed at molecular level. The hydrolysis can be base catalyzed, in which OH negative attacks the metal center, or acid catalyzed, in which H positive helps break the MOR bond. Finally, we heat or calcine the gel to burn off the organic and get the pure oxide. So the example of alkoxides are MgAl2O4 with synthesis using sol gel method. In this method, we take magnesium methoxide and aluminium butoxide. When they undergo hydrolysis and condensation, they form an amorphous gel, and the gel decomposes to give very fine spinal particles at just 250 degrees Celsius, which was previously obtained at a very high temperature, approximately very higher temperature compared to this. Which was 1500 degrees Celsius for heating for several days for solid state synthesis. The only drawback is that alkoxides are expensive and are sensitive to moisture. So the other is ITO coating, or indium tin oxide coating. ITO is a transparent conductor which is used in touch screens, solar panels, and building energy controlled glass. To make ITO coating, we use indium and tin alkoxide. We either pour the sol on the substrate or dip the substrate into the precursor. After drying and heating, we get a thin, clear, perfectly adherent ITO coating. The other important coating made by Sol Gel are Ta2O5 from TaOET whole 5 used in capacitors, and SiO2 TiO2 coating used as anti-reflective films on solar cells. A major challenge in coating technology is cracking. Gel lose a lot of volume when they dry because of the vaporization of what is trapped between the cross linking of the gel. So the thin coating can handle this shrinkage better, so they stay smooth and crack free, but thick coatings can crack because of the internal stresses. So overall, soft chemistry methods like the alkoxide sol gel route solve the biggest problem of the solid state reaction, which is poor atomic level mixing. They give purer, more homogeneous product, allow us to make the special shapes like coating, and often require much lower temperature. The only challenge is that their cost sensitivity of reagent handling, and the need for optimized conditions. Another very important soft chemistry approach is the formation of sols and gels from inorganic oxides and hydroxides simply by adjusting the pH of the solution. This works especially well for the elements like aluminium, whose ions change structure depending on whether the solution is acidic, neutral, or basic. So, let us discuss this using the aluminium as the example. So, in acidic solution, aluminium exists as a simple hydrated cation, aluminium hexahydrate with the overall plus 3 charge. In strongly basic solution, the same aluminium form anionic hydroxide, which is AlOH4 whole 4 negative. This ability to dissolve in both acids and bases but not in the middle pH range is why aluminium oxide is called amphoteric. At intermediate pH, the aluminium forms a huge variety of polymeric multication oxyhydroxide species, and these are the basis of sol gel chemistry because they form nanoparticles that come together to make gels. As base is added slowly to an acidic Al3 positive solution, several hydrolysis steps occur. At intermediate pH, large polymeric aluminium clusters appear. One famous example is the big Al13 polycation, which is listed here in the slide, and these multi-metal clusters form a colloidal sol, a liquid containing tiny nanoparticle species. As the pH increases a bit more, these nanoparticles starts to stick together, which is coalescence, and form a gelatinous hydrous oxide. It looks like a jelly solid but is actually a hydrated hydroxide with an uncertain non-crystalline structure. If the pH is increased even further, this gelatinous precipitate redissolves and forms complex anionic species such as AlO4 negative. So entire chemistry depends on pH, and that's exactly what the figure is showing here. Uh, the figure shows the pH cycle of aluminium, how aluminium species change as we move from acidic to basic solution. If we walk through this clockwise figure, the acidic region, the left side of the circle, we start with the aluminium hexahydrate, the simple hydrated cation in acid. As we add hydroxide, from adding base, the hydrolysis begins. At intermediate pH, the bottom region, we get partially hydrolyzed species like these. And these combine to form gelatinous hydrous oxide. This is the sol gel region. The basic region, the right side of the circle, further addition of OH negative dissolve the gel to form aluminium hydroxide AlO4, AlOH whole 4 minus. And I not whole 4, AlOH4 negative, an anionic complex. Heating the gel forms the hydrous from the hydrous oxide. Heating drives off the water and form Al2O3, and which is crystalline aluminium. So this picture is basically telling us in acid aluminium is a cation, in neutral pH it forms sols and gels, in base it becomes an anion, and with heat the gel turns into oxide, and this is a crucial for sol gel chemistry. So aluminium is not only the element that behaves this way. Many elements with intermediate electronegativity show complex aqueous chemistries. For example, zinc behaves almost exactly like aluminium, which is amphoteric in nature, cation like aluminium, and it forms a cation and a colloid and then an anion on changing pH. Silicon forms many complex silicate ions, and boron form borates, phosphorus form phosphates. Some of these polymeric species are hard to identify directly, but in silicates and phosphates they can be separated and studied using chromatography. So the oxides like Al2O3, SiO2, Fe2, Fe2O3, and zirconium oxide and Y2O3 are ideal for pH controlled sol gel chemistry because their solubility and structure changes with pH. This lets us mix the different sols to make the complex oxide. Use oxide powders as starting material and make material in more useful forms like thin films, fibers, coatings, ceramic shapes. A very useful application is making micron thick coating. For example, silica sole gel coatings can be applied onto stainless steel mesh to increase its oxidation resistance. Coating can be made by dip coating, dipping the substrate into the sole, or spin coating, the spinning the sole onto the surface of to get a thin, even layer. These methods are excellent because they give smooth, uniform, thin films that would be impossible to make with high temperature solid state reactions. So, in essence, by simply controlling pH, we can tune the aluminium and other similar elements to behave as cations, colloids, or anions, creating perfect conditions for sol gel synthesis, especially for making coatings, thin films, and complex oxide materials with high chemical homogeneity. Now let's discuss the zeolites, which are extremely important materials in chemistry, catalysis, and industry. Zeolites are aluminosilicate frameworks, basically a 3D network of aluminium, silicon, and oxygen atoms. The special thing about this network is that it contains large interconnected pores and channels, almost like a sponge made of crystals. Because of these channels, ion can move in and out easily, used in ion exchange, and a small organic molecule can enter the pores, which is basis for catalysis inside these channels. So why these are used? So this is why the zeolites are used as molecular sieves, acid catalyst, and shape selective catalysis. Only molecules of certain shape can enter the pores, which is the basis for this property. And recently related materials like ALPOs, which are aluminophosphates, and MCM phases have been developed, and these have even larger pore size than normal zeolites. So zeolites are made using sol gel methods followed by hydrothermal treatment, meaning heating in the high pressure water. A typical reaction involves mixing alkaline solution of aluminium and silicon, whose reaction is shown in this slide as this, in which the reactant mixed to give gel. And at room temperature, which is 25 degrees Celsius, the mixture forms a gel because tiny aluminosilicate species join together. Then this gel is placed in an autoclave and heated at 100 to 200 degrees Celsius under pressure. Under hydrothermal condition, the atoms slowly reorganize to form the crystalline zeolite network. So, the type of zeolite formed depends on the composition ratio of aluminium and silicon, the pH, the temperature and pressure, and most importantly, the template molecule used. The template are usually alkyl ammonium ions, which are shown here. These large organic ions sit inside the pores during the growth and shape the cavity. Basically, the zeolite grows around the template like jelly setting around a mold. The template provides the direction or the growing this defines the growing nature of zeolites. So after crystallization, the template must be removed, and when uh, after crystallization, the template needed to be removed, and we heat the zeolite to 300 to 400 degrees Celsius. The organic template burns away, leaving the empty channels open. Even though these frameworks are not thermodynamically stable, they are kinetically stable up to 300 to 400 degrees Celsius, which is enough for industrial use. So this picture shows the steps in which the zeolite is synthesized. The mixing stage, the top of this image, shows two beakers with silica and aluminium source, and the one with alkali hydroxide solution. These are mixed together to form a homogeneous solution, and the mixture contain all the ingredient needed for forming aluminosilicate framework. And this section shows three small beakers with particle inside at different stages. It is labeled as 2A, 2B, and 2C. 2A, at first the mixture becomes an amorphous gel. The tiny particles are randomly dispersed and there is no crystal orders, which represent by the 2A, which are reactant in the amorphous phase. For 2B, the small nuclei of zeolite starts to appear. These are the first tiny crystals. And for 2C, finally the amorphous gel is converted into real zeolite crystals which grow and replace the gel. This is the crystallization phase. And the yellow arrow labeled heating 100 to 200 degrees Celsius shows the hydrothermal treatment step. So heating plus water pressure drives the crystallization. Final, after filtration, washing and drying, we obtain the final zeolite crystal structure shown on the right, which is this. The image shows the open framework, the channels and cavities are clearly visible. This is the structure responsible for all zeolites' catalytic and molecular sieve properties. So the figure shows the life cycle of the zeolite. The mixture to gel formation, gel to nuclei, nuclei to crystal growth, and from crystal growth to the removal of template and final porous framework is obtained. So let us discuss what is hydrothermal synthesis and solvothermal synthesis. So hydrothermal synthesis simply means heating reactants in water or steam at a very high temperature and pressure. Water here plays two roles. It acts as a solvent and the solubility of reactant depend on the temperature and pressure. And the second one is it acts as a pressure transmitting medium, creating a high pressure environment inside the reactor. To perform hydrothermal reactions, we use a PTFE lined autoclave, also known as hydrothermal bomb. We put the reactants and water inside, seal it, and place it in a oven at temperature usually between 100 to 500 degrees Celsius. The picture on the right hand side shows hydrothermal reactor and its So the image on the left hand side depicts the hydrothermal reactor and its component. The shiny metal cylinder is the stainless steel reactor body. It holds the pressure from inside. Inside it we place a Teflon PTFE PPL inner sleeve. This is important because the chemical should not touch the steel. The reactor has a stainless steel cap and spacers to keep everything tight and assembled. So once assembled, the whole unit goes on into an oven. The heating jacket or mantle, it controls the temperature of the reactor. And in short, the steel gives pressure strength, the PTFE or PPL gives the chemical resistance, and the oven gives the temperature. On the right hand side, the diagram shows how the crystal grow in the hydrothermal temperature gradient. There are two zones inside the autoclave. Uh, the hot zone is the bottom one depicted in orange color. The temperature is high and the solid starting material dissolves in the hot water. The solution becomes enriched in the dissolved particle. In the cool zone, the top zone depicted by blue color, it is of lower temperature and the solubility decreases. Dissolved material crystallizes onto the seed crystals hanging there. So, which is depicted by this shape. So, this creates a continuous cycle and the hot zone dissolves the material. The hot solution rises up. At the cool zone, the material deposits on the seed and the cold solution falls back down and the cycle repeats. This is how large quartz crystals, which are of SiO2, made hydrothermally. Now, uh, now the pressure temperature relation. For now we move on to the this image with the graph and bomb drawing. So this explain how the pressure builds inside the vessel based on the temperature. So on the left side is the PT diagram of water. The curve AB shows the saturated stem line, and the below line is the steam. the saturated steam line it AB shows, and the below the line is steam, and above the line is liquid water. And beyond 374 degrees Celsius, point B, which is water becomes supercritical. That is, there is no difference between liquid and gas for liquid as gas existence state of water. On the right, we see how the hydrothermal bomb works. Starting material is kept at the hotter bottom, and water fills the vessels, and the seed crystals are placed at the top cooler top. And SiO2 dissolves better at higher temperature. It dissolves at the bottom and crystallizes at the top, as we have already discussed earlier. The applications of hydrothermal synthesis are extreme. It is extreme. The hydrothermal method are extremely useful because they allow us to make the material that would otherwise require very high temperature. Some example includes the zeolite synthesis. The final stage of zeolite formation needs hydrothermal heating to convert aluminosilicate gel into crystalline frameworks. The quartz SiO2 crystals used in electronics and watches are grown using temperature gradient hydrothermal methods. The NaOH is used as a mineralizer, meaning it increases the solubility of SiO2 so that the process becomes much faster. And the making of oxides at lower temperature, example the magnetoplumbite, which we have discussed here. This is the magnetoplumbite, and normally needs 1250 degrees Celsius in the solid state synthesis, but in hydrothermally it can be made by 325 degrees Celsius. Also, the Bayer's process, which is the extraction of alumina, that is the commercial scale hydrothermal process that is used to extract the aluminium oxide from bauxite ore. Now, for discussing this image, the image that is depicted on the left side, this image shows how the Bayer process is used to extract pure alumina from bauxite. Here's what happens. Bauxite, which is impure AlOH thrice, is crushed. First it is crushed, and it is dissolved hydrothermally in hot NaOH. And it is the bauxite impure is crushed and it is dissolved in hot NaOH at in a pressure vessel at 140 to 240 degrees Celsius. The insoluble impurities from the red mud form the red mud iron oxides, and it is filtered, and the solution contains NaAlOH4, which is aqueous in nature, and by cooling and adding this AlOH3 seeds the gibbsite, this with the chemical formula of this it precipitates, and gibbsite is heated in a rotatory kiln to give alpha Al2O3, and this alumina goes to smelter to make the aluminium metal. So Bayer's process is basically hydrothermal dissolution. Here hydrothermal dissolution is done, and then precipitation, and then heating and extraction of pure alumina. Now, solvothermal synthesis is very similar to hydrothermal synthesis, except it uses the organic solvent or supercritical solvent mixtures instead of water. For example, the Li2MnSiO4, a battery cathode material, was synthesized phase pure at 300 degrees Celsius and 38 megapascal in just 5 minutes, in just not even 15 but 5 minutes, using supercritical water ethanol. And this material is extremely hard to make using traditional solid state methods because Mn2 positive oxidizes easily. The high temperature are required, and Mn2 positive is too large to easily fit into the tetrahedral sites. So solvothermal conditions solve all these problems by providing a controlled high pressure, high temperature liquid environment. So overall, hydrothermal and solvothermal methods allows us to make crystals, zeolites, oxides, phases, and even battery materials at temperature far lower than solid state reactions. The key idea is getting high temperature and high pressure inside the liquid water or supercritical solvents, which dissolve and transport the material much more efficiently than dry solids. So this concludes our presentation. this concludes our presentation. And in this presentation, we learned how the solid state reactions occurs and shake and bake methods, which are normally called in shake and bake method, how they are used to make the solids that are of very much physical use, and how the new methods are developed like low temperature method or chemi dose methods, which are used, which are more gentle, clean, and great for films and nanomaterial, which compensates the high temperature requirement that is usually required to carry out the solid state reactions. Thank you.